and I'd like to briefly introduce Saad. Saad is with our Palantir folks, and I never quite know how to introduce Saad because I believe his technical title is something like deployment specialist, which, as he has noted to me in the past, not everyone knows what that is, myself included. I like to think of Saad as sort of a cross between a systems engineer who builds high performance computing systems and a data scientist who sort of gets down with some data and some statistical and machine learning techniques. So I think he's probably in the crosshair of a data engineer. With that said, Saad, thank you so much for taking the time to tell us a little bit about how we can optimize our work in the Enclave, and take it away.
Sure. Thank you, Sean, for the introduction. We're going to talk in this training about build performance. So if you have access to the Enclave and you started running analysis in Python, R, SQL, or even Contour, which it looks like a lot of you already tried. We hope that you'll find this information helpful. Some of this information was presented during the collaborative analytics meeting last week and the clinical scenario this week. So today there will be some repetition of the principles, but hopefully with more practical examples. And so why it's important, let me open the homepage real quick. And so as you can see from the homepage, data is getting bigger. The size of data hosted in the Enclave increases basically after each release. So roughly on a weekly basis, we're at about 5 billion rows. Some of the domain tables, if you started using them, like the lab measurements, is 2.3 billion rows. So it is becoming important to kind of follow some good practices when writing code to conduct analysis in the Enclave, whether it's using Code Workbook or even using Contour, so you can ensure smooth development experience and avoid suffering from long build times. So this is kind of today's agenda. I'm gonna run through a brief introduction of Spark. Just on a high level, Spark is the compute engine that the Enclave uses. So while you don't need to be an expert and know the ins and outs of Spark to do analysis, it's kind of helpful to have a mental model of how it works because it's different than traditional relational databases. Also, so once we do that, I'm going to walk you through some of the a number of checks, like about 10 checks and principles that you should look for if you feel like your analysis is running slow or if you have out of memory errors. And along with that, we're going to be jumping into practical examples on a code workbook to show you how it's done in practice. And so in terms of resources, in addition to today, and maybe hopefully we'll run this session, we'll have maybe other iterations. You have a document in the training module that walks through the principles I'm going to talk about today. So if you go from the homepage to the training material, just so I can point to it, and then click on the training portal. One of the training modules is called Troubleshooting Slow Performance. And if you open the module, you'll have a link taking you to this tutorial, which is not really a tutorial, but more like a number of troubleshooting steps along with coding examples. So whenever you have a build that is slow or your analysis is giving you some memory errors or running much slower than expected, one of the things you can do is check out some of the tips and good practices here and make sure you're doing the things that are described in this document. And obviously, if you go through these steps and you still have issues, you should definitely report an issue and reach out to us, and we'll look into your analysis and we'll try to help you troubleshoot it and make it faster. The other thing for people who want to get into the weeds and have more advanced information about the code optimization in Spark, within the Enclave, there's this Spark optimization course, which you can follow if you want more detail. So I just wanted to point that out. We're not going to cover that today. So going back here to briefly introduce Spark. Spark is the computational framework used for parallel data processing on clusters. Essentially, all the queries, anything you do in the Enclave, whether you use Contour or write code in Code Workbook to analyze data, all these queries run in this framework and use Spark. It's an open source software maintained by the Apache Software Foundation. So here is kind of a high level of the parallel processing principle that Spark uses. It's a little bit of a simplified picture, but just to give you a mental model. So all the computations that you run on a data set or a data frame is distributed across across the cluster. So essentially, when we're using Spark within the Enclave, we're taking advantage of parallel processing. We're distributing our computations across different clusters to have a faster execution time. In addition to that, the way data sets are stored, so the way tables in the Enclave are stored, are also in a distributed fashion. So every data set in the Enclave is saved into what we call multiple partitions or multiple files, which are, the format is a Parquet, which is kind of an optimized format for Spark. And so the reason data sets are split and saved into several partitions is also to kind of optimize query time and execution time when you're running computations within the Enclave. And so as a result of this model of saving data sets, the way you run queries such as a filter is, for example, here, if we have a data set where we want to filter to only people of the age 18 or older, this query is going to run in parallel across these different files and partitions. So the query can be operated on independently by different executor machines. And that kind of ensures a little bit of, it ensures a faster execution, especially when we deal with data at large scale. However, because of this model as well, some other queries, such as group by queries and aggregations, the queries cannot run independently because Spark sort of have to look at all the partitions and kind of merge them and swap them into a common place so that these type of queries are executed. So if we run a group by query, Spark performs what we call a shuffle, meaning that rows are swapped between partitions so that this query is enabled. And so these are some examples of these type of queries that require a shuffle. The most common ones are joins and group bys, and for example, running distinct for deduplication. And the reason I'm mentioning that in the beginning is that because these operations require a shuffle, they tend to be more expensive than other operations, such as simply filtering data sets. And so it's good to be aware of that when writing code and trying as much as possible to minimize these operations or put them in an order that helps for the execution and for performance. And so now we're going to move into a number of practical things that you can do if your build is running much slower than expected, or if you're getting out of memory errors. And one of the most basic things and very helpful things that you can do is essentially just to reduce the amount of data you operate on. So when you operate on things like a measurement table, which is 2.3 billion rows, you probably don't need all the columns from that measurement table to run your analysis. And you probably don't need all the rows as well. So dropping the columns you don't need and performing filters early on in your analysis before running the analysis might be helpful. And so let me jump into a workbook in which I put some examples of such things. So I'm looking here at the notional SIMPOF data, and we have a data set called procedure occurrence, which records the procedures. If we open this data set, we can see it's 13.9 million rows. And I'll get later into how it's saved and partitioned. But just to make the examples more relevant here, I made this data sets bigger by kind of duplicating the rows, because some of the principles I'm talking about today start making a difference when the data becomes larger. And so here I built a data set which is much bigger. So this one is 887 million rows. And so now we can start seeing the difference between these two queries. So the first query here is essentially just grabbing the input data set. This is Python, by the way. In this workbook, we're going to run through examples in the 3 languages, R, Python, and SQL. I try to mix it up because people have different backgrounds. We'll also try to make a more comprehensive workbooks with each one of these languages so that you can take a look after the presentation. But this is a basic query in Python using the PySpark library, where we're just grabbing the procedure occurrence table. We are doing some renaming of columns. And then we're doing some data processing. Namely, here we are looking at the procedure name column. And if the procedure name column contains the string oxygen, then we're going to tag it as an oxygen-related procedures. Otherwise, we're going to leave it as is. Another processing thing we do here is just creating a new column by concatenating 2 existing columns, and also doing creating another column, which is a flag telling us whether the procedure is related to that has the word cardiac in it. So simple data processing, renaming columns, doing data processing, and then doing an aggregation on the procedure name to get the counts of all the procedures by the procedure name and the unique count of patient IDs. So this is running on this query runs on an more than 800 million rows. If I open the data set, I ran the query before the presentation to save some time. And if you look at the history tab here, so the history tab gives you the history of all the builds. This one ran in 2 minutes, a little more than 2 minutes, which is still quite fast given the size of the input data. But let's compare with this other query here, which is exactly the same logic. But what we're adding here is that we're only given this big data set, procedure occurrence bigger, we're only selecting the 2 columns that we need early on, procedure concept name and person ID. I commented this out, but this also helps if we don't need some of the rows for which that contains surgical, we can apply extra filters to just filter to the data we need. And then I'm rerunning exactly the same analysis, renaming a couple columns, doing some data processing, and running an aggregation. And if we look at the, let's look at the preview of the results. And looking at the history, we can see that this one only ran in 1 minute. Now you may think between 1 and 2 minutes, it's not a big difference, but when we start doing more complex data processing, and when we start dealing with larger data sets, this actually can make a big difference. So the takeaway here is filtering to only the data you need by dropping the columns that you don't need and doing all the filters early on, and then applying your data processing. So that's the first thing, the first kind of check that you want to look at. The other thing, still in the theme of reducing the amount of data operated on, is the order of operations in which we do our processing. And let's look at another example here now in SQL. Where this is a SQL in which we're taking as inputs the condition occurrence table, a measurement table, and we are joining these two tables on the person ID. So we're joining them to get a data set with measurements as well as conditions. And then we are joining with a data set called My Concepts, which, if we check here, contains some of the concept IDs that I want to run my analysis on. And I think they're around 200 concepts. They're related to this code set ID. But essentially what we're doing here is we're performing a join between the condition occurrence and the measurement table. This join results in a large table because of the number of records. If we look at condition occurrence, we have 14 million rows, and the measurement table that I'm using has 108 million rows. I'm trying to zoom in a little bit more. And so when we join these two tables first, we can expect that our resulting data set becomes bigger or big. And then the second step I'm doing here is joining with the concepts to essentially only keep the concept IDs that I need. So this, this theoretically should reduce the number of rows of my resulting data set. Doing things in this order, if we check the runtime of this, this took about 3 minutes to realize, to do these two consecutive inner joins. In this second example here, I'm doing exactly the same thing, but I'm changing the order. Namely, first, I am joining my condition table to the list of my concepts to keep only the records I need, the records that belong to my list of concepts. So the resulting data set of this join will be smaller to start with. And then I can join with the measurement table to get the records, both measurements and conditions that I'm interested in. And this query, I ran it also earlier before this presentation. If we check the runtime, it should be much better. So this one was only 1 minute. And so again, when we start dealing with more complex operations and larger data sets, this difference becomes bigger and matters. And so the key takeaway here is the order matters in performance, and doing things like first joining with a small data set to get a smaller intermediary data set before performing subsequent join helps the performance. The second check here is cleaning the data. And so essentially when, so there are two things here in terms of cleaning the data. One is standardizing your data set. So let me see if I have an example in here. If we look at my procedure occurrence data set, the bigger one that I created, And I want to look at it quickly in Contour to look at the procedure names. Because something I did on purpose here is I kind of mixed up some of the string values to have like more variety of strings. So if let's look at it in Contour, it will make more sense. Let me filter to only the values, the concept names. So procedure concept name, only the ones that contain the word surgical. And now let's look at the histogram of these values. We'll give it some time to load since it's a large 800 million data sets. It will take a little longer to load. But the idea here is that let me look at the right. The idea here is that sometimes in your columns, you have some values which are essentially the same. But some of them are in lowercase, some of them are in higher case, and that actually creates a lot of overhead and hurts the performance when running queries on these data sets. And so harmonizing values and standardizing them, especially string values, can make a big difference in the runtime. So as you can see here, I have things like surgical lowercase and surgical all capital letters, and they essentially mean the same thing. So you will benefit a lot from, if you know your data and you do some basic exploration in Contour, for example, you explore your values and you see that a lot of values are the same, but they're spelled differently. You will gain in performance by harmonizing these values. And so this is an example where I'm kind of standardizing the values. So I'm looking at the procedure concept name, and I am replacing for each value in the procedure concept name column, I'm replacing all the surgical values with capital letter. And that should be, that should basically speed up your runtime. The other thing that in terms of cleaning data that helps is the data types. There are data types which are more efficient than others. So in order of compute cost, for example, integers are more efficient than long, which are more efficient than doubles and strings. So going back to my input data set here, procedure occurrence, I can see that there are some values, some columns such as person ID, which is a double, which should essentially be an integer. Just trying to find other examples where, for example, procedure source value, we could cast it into an integer instead of a string, and that will help performance a lot. This is only possible, obviously, when changing the type of your column doesn't change the meaning of the data or doesn't change the results. So things like here, person ID, procedure occurrence ID, where they're stored as double, where we can probably cast them as integers and not lose the meaning of the data, and the results of our analysis will not change. We will definitely gain in speed by casting these values. Other examples here are procedure source value, which are essentially numerical values, integers, and they're stored as strings. So these are things that we can do to help run our query faster. So I'm trying to find an example where we're doing this data types. So in this example here, what I'm doing is I'm taking this column procedure occurrence, and which is stored as a string, and I'm casting it as an integer. This is Python code. And I'm doing the data processing that I did earlier on. And this should help running the query much faster. So that was it about cleaning data. Now, I know on the poll, some of you mentioned that they are not familiar with the Spike libraries, such as PySpark and SparkR. So these are libraries, PySpark and SparkR. These are Python and R libraries that interact with Spark and give you some functionality that is similar to Pandas. If you're used to work with data frames in Python, or similar to native R data frames. And the reason why this is important is that if you use regular Pandas or native R to manipulate data frame, the logic is not your logic is executed in the driver of a single processor, and that could be very slow. It could result in out-of-memory errors when the data becomes too big. So you can get away with using Pandas or manipulating data frames using regular R, native R, when the data is small enough. But when it becomes too big, your performance starts suffering. And so moving to PySpark or SparkR as much as possible will help you benefit from the power of the entire compute cluster and parallel computing. So there's some examples here that I tried to do where this is a simple aggregation using the initial procedure occurrence table that has about 19 million rows, where I'm converting the table into Pandas, and I'm using my Pandas syntax to do a simple aggregation. And that actually gives me a memory error and says the data is too large, while doing exactly the same thing using Spark, using PySpark in this case, on a bigger data set, ran in about 2 to 3 minutes. In the Enclave, we provided some resources. If you click on the documentation and go to Code Workbook, refresh the page. If you go to PySpark reference, there is a PySpark syntax cheat sheet for people who use Python with the most commonly used operations. So you can do this switch between Pandas and Spark easily. For SparkR, you can look up the SparkR documentation, which is available online, which gives you a very similar syntax and examples for how to manipulate data frames using this library SparkR if you're using R. So the advice is, when you start, obviously, people might not be familiar with these libraries. And so you may want to start using your regular coding language. But when you start hitting memory issues, learning a little bit of the syntax of Spark might help a lot speed up your code and help you in terms of productivity. So that's on Spark and SparkR. Obviously, there are cases where you still need to use your R libraries, or you still need to use Pandas, or maybe you don't have time to kind of adjust. In that case, we still recommend that at least early on in the analysis, that you manipulate your input data frames using Spark and do all your filtering and selecting columns and filtering to only the rows you need using Spark. And then once you have that reduced data set, you can do a conversion to a regular data frame as you know it, either in pandas or in R. The keyword here for this is an R example where the keyword is collect. There's the same thing, same keyword you can use for Python. In fact, when you go back to this document, we provide some syntax for Python and for Spark. So for Python, you can do 2 pandas to convert your Spark data frame into pandas data frame. For R, you just do you use the keyword collect, and once you do that after minimizing your data set. Once you minimize your data set, you can convert to a local data frame and then use the libraries that you're used to, either dplyr, for example, in R or other pandas libraries, and do your data processing and analysis. And that should hopefully help run your analysis much faster, even though you don't use a full PySpark or Spark R code. The other thing that is important to do is, see here I mentioned, I showed these conversions back and forth between a local data frame and Spark data frame. So for example, in Python, between a Spark data frame and a pandas data frame. These conversions actually are time consuming. And so you want to minimize them as much as possible. You want to maybe do these conversions early on in your code, and you don't want to do them regularly and multiple times within the same transformation, because moving data between locally between the distributed store and the single VM is time consuming and scales with the number of rows and columns. So that could hurt your performance a lot. So when you're doing these conversions using collect or 2 pandas, we recommend that you minimize them to maybe just 1 conversion or a few conversions early on in your analysis. The fourth check here is in case you're using user-defined functions. So these are for people who are manipulating Spark data frame, whether these are data frames in whether you're using Python or R. UDFs or user-defined functions are essentially functions that apply a transformation on each row of your data set. So a basic example here is a square user-defined function. So like converting the values of my column to their squared values. These tend to be super slow. They can be, in some cases, up to 1,000 times slower than, and we have alternatives and built-in Spark functions that do the same thing. So instead of defining your own UDF to do these type of transformations, you should check out the PySpark or Spark R libraries for equivalent functions that could do the same job. So an example here that I'm showing in this code, and this one is using Python. It's basically taking the procedure occurrence data set, and we're taking the procedure concept named column, and we're trimming the white space. And I've defined this UDF here in my global code on the right-hand side of my code workbook. So this is my user-defined function. I'm telling my code to essentially for each row replace an empty space with no space. So trimming the space using a user-defined function can be incredibly slow, where doing the same thing but using this function regex replace is from the PySpark SQL function library, does the same job but much faster. So again, in the code workbook documentations, we have cheat sheets for all these built-in functions, both for R and Python. So that's on UDFs. The key takeaway is avoid them as much as possible. Sometimes it's hard to avoid them when the built-in function doesn't exist, but when they exist, they should be avoided. Now the fifth check is for null joins. So what are null joins? They're basically a situation where you're joining onto columns where many of the row values are null and missing values. And this can hugely increase memory consumption. So doing things as simple as inspecting your data early on and looking for data, looking for your column and see if there are the percentage of null values and filtering them out before performing the join can help a lot. And I think here we have an example in this workbook for the null joins. So here I have a visit occurrence data set. And if I open it, when you look at the columns here, you can see on the left-hand side, you can see the percentage of nulls for each columns. And here I created a data set with almost 33% of the values in this column person ID are null, so about a third. And I'm joining that with another data set, drug exposure, where if we open it and look at the columns, about a quarter of the person ID values are null. So when I'm performing this join here, this is very inefficient because I'm doing a join on person ID. So I'm joining my visit occurrence table with my drug exposure table, and I'm joining on a column for which in both data sets has a high percentage of null values. That could be very inefficient and slow. And the alternative here is to filter out using things like this function call and remove all the rows for which the value of person ID is null. For both visits and drugs, I'm doing the same thing where I'm filtering out the null values before performing the join. Can be a much faster query. So that's on null joins. So the key takeaway is remove the null values or the rows for which you have null values before performing the join, especially for if the null values are in the column, the key column that you're joining on. The sixth check that you can do here is, so joins tend to be, in general, expensive operations because they require shuffling. They can be more expensive and time consuming in the case where you're joining a big data set with a much smaller one. And typical examples of this are when you're joining a domain table, such as measurement, with a concept IDs table that has a list of like a few concept IDs to just get the measurement records that you need. This can be inefficient when doing a regular join, like the way without any intervention, because essentially there is a lot of duplication and shuffling. For each partition of the big data set, you're doing a join and there's like a lot of overhead and shuffling. And you can gain a lot of efficiency when you use a broadcast, what we call a broadcast join. And a broadcast join is essentially copying the right hand side data set, the smaller data set, kind of next to each partition of the bigger data set. And so that ensures that in this case, there is no shuffling that needs to be done, and the query can run much faster. And when you're using R or Python, it's something as simple as adding a keyword called broadcast that can help performance. And here we have an example of a broadcast join. So this is R. And what I'm doing here, I'm joining two tables, my condition occurrence table, which is the records of all the conditions per person ID, and a concept set members table in which I want to filter to some specific concepts. So in this R code, I'm taking my concept set members table. Let me actually maximize this so that it's easier to read. And I'm filtering to this code set ID. I'm filtering my concept set members table to this code set ID. And then I'm performing a join with this large condition occurrence table. So again, we have a large data set condition occurrence joined with a much smaller concept set members data set on the concept ID. So a better way to make this faster is to, because we know that my concept set members table that I'm joining here, especially after I filter to only this code set ID, is a much smaller table. So this is generally a good candidate for a broadcast join. So the way to do it here in R is to just add the keyword hint and the keyword broadcast to my data set, the concept sets data set. And that usually does the trick. And the join should be much faster because there is no shuffle required in this example. So key takeaway: broadcast joins are usually good candidates when you're joining a large data set to a much smaller one. Now let's talk about repartitioning. I mentioned earlier in this presentation that data sets are saved into multiple partitions. And let me show an example on how to check for that. If we go to the data catalog, and let's go to the notional SIMPAF data. And let me, for example, click at condition occurrence. Let me open two data sets, condition occurrence and maybe drug exposure. So looking at the dataset UI here, condition occurrence, there is a tab called Details tab, which gives me more information about how this dataset is stored and some additional information about the schema. If we look at the Details tab, you can see that the size, so it's a 14.8 million rows dataset. The size of this dataset is 274 megabytes. And when you look at files, files is basically the number of partitions. So what this is telling you is that the condition occurrence data set is saved into two different partitions. And if we click on the files file section here, you can see these two data sets here and the size of each one of them. So these are my two partitions. So and one of is 2.6 kilobytes and the other one is 274 megabytes. And so in terms of partitioning, in general, this is a rule of thumb. It's generally the case, although there are some exceptions, where you want to aim for basically a ratio, or each partition should be roughly 128 megabytes. So you want to have a number of partitions that kind of achieves this 128 megabyte per partitions. The idea here is that if you have too many partitions, if your data set has too many, especially small partitions, that can hurt. It takes Spark much longer to read and query data from each one of these partitions. And so if we go back to our condition occurrence table, we can see here that the size is 274 megabytes. And it's split roughly into two partitions, which is, we can say is a well-partitioned data set because you have roughly 128, it's like 128 megabytes per partition. If we look at drug exposure, on the other hand, and let's look at the details tab. So here we have 6.3 million rows. The total size of the data set is 124 megabytes. However, we have about 200 partitions. And so when we look at the files, we can see all the different partitions, and they're all like small partitions of about 600 kilobytes, and you can look at the size of each one of them. So this is a data set where we would say it's kind of poorly partitioned. It starts to matter when you have some code where you're running a transformation and it's taking you a long time to, it's taking the code a long time to run. And in order to basically fix that, what you can do is change the number of partitions, in this case to a smaller number, which we call repartitioning, and that generally helps to run your query much faster. So I have an example here of repartitioning. So we're starting with a measurement table, and let's check quickly the number of partitions and the size. And if we look at the details, 3.4 million rows, about 200 partitions, but the total size is 61 megabyte. Now remember, ideally we want to aim for one partition equals roughly 128 megabytes. So you can see that we can actually put the whole data set into one partition. It won't necessarily hurt the performance. You might actually make it better if you're doing some advanced computation. So this is a simple aggregation. This is our code where we're taking the measurement table that has 200 partitions, and we're just grouping by and looking at the count of the patients. So grouping by person ID and measurement concept name, and just computing the counts. So something in order to improve the speed of this and improve the performance, since we know that measurement table is poorly partitioned, we can use the keyword repartition. And in this case, we can probably fit our data sets into one partition. And by doing that, and then performing our computation or aggregation or analysis, this can run much faster. So repartitioning and changing partition is a bit of an art, and there is a trade-off. When you have too many partitions, that generally hurts the query time, so querying data. But when you have too few partitions and your data set starts being large, you may start running into memory issues. So there is a balance, and this is why we sometimes recommend that 128 megabytes per partition. Generally, we don't look into doing repartitioning until we have tried all the other tips that we've mentioned earlier. And if we're still suffering from performance, then maybe that's because the data set is poorly partitioned, and in that case, we can do repartitioning. If we go back to the tutorial that I mentioned earlier, on the dataset repartitioning section, we're providing the syntax, whether you're using SQL, Python, or R, where essentially the keyword is just .repartition for Python, for example, and that does the trick. You can also do a repartitioning by key. And what I mean by that is, if you know that you're going to perform a lot of the queries and a lot of the aggregations or join on a specific column, for example, person ID, it makes sense to actually repartition not by providing a fixed number of partitions, but by doing a repartition by person ID. That kind of helps optimize your queries, because you're going to be doing a lot of the joins or a lot of the filtering or aggregations on that specific column. So that's on repartitioning. I'll move quickly on the salted join tip, because I know we're close to the hour. Essentially here, when you're doing a join and you're joining a large table with many entries per key to a smaller table with few entries per key, that can be quite inefficient, and this could be a good candidate for what we call a salted join. And so the way to check for that is usually using Contour or Code Workbook. You can go to Contour and do analyze. And if you look at a histogram on the key that you're joining on, so let's say my key will be person ID, I can do a quick check to see if my data set is kind of imbalanced or well balanced. And if it's imbalanced, if we have too many records per key, then we can consider using a salted join. Here we see that the distribution, we can also look at the distribution board, which also gives a similar information. In this case, it's not like terribly imbalanced. We should look at the whole distribution, but this might not be a good candidate for a salted join. But if you have a key or a few keys where you have way too many records, and then you have other values for which you have one or like very few records on the same column, then that's what we call an imbalanced or skewed data set. And performing a salted join might help enhance the performance. And again, in the tutorial, we're providing the syntax. So we have an example in SQL for how to perform a salted join. So feel free to check that out. And then just to wrap it up, I know I went a little bit fast and I didn't show all the run times for all these example queries. I will send an example of this workbook after the presentation. But a good way to ensure and like improve the iteration time and figure out what the issue is when you're developing code within Code Workbook is to kind of just split your transform into multiple smaller transformations. So when you have a function in Code Workbook, this is a smaller one, but you may have a function that does many things at a time, like filters, aggregations, then a join, then running a dplyr, analysis, and doing some graphs. And you run that analysis and it's taking way too much time to run, or it's returning memory errors. It generally helps to split your transformations into different steps. On one hand, it helps with figuring out the bottleneck and what's causing the performance to be slow. And on the other hand, it's just sometimes the right thing to do, not to do too many transformations in too many operations within the same function. Something that also helps is when you're starting to develop in Code Workbook, it's generally a good practice to start with input datasets, which are just a sample of the domain table. So you can just like, for the measurement table, get a sample of maybe a few million rows, and then run your analysis on that sample. And then when you ensure that your code runs smoothly, that you don't have any syntax errors, that your analysis is sound, then you can run on the bigger version, on the larger data set, which is larger. And this will help with iteration and reduce the amount of frustration that comes from using very large data sets. And if you check the knowledge store, Sean has an example where you can, Sean has a template that does this sampling to a smaller number of rows. So you can use that to start your analysis. And then lastly, when you have out of memory errors, and these are just some examples of these errors, possible reasons are generally that you're running your transformations in pandas and native R, and maybe you need to switch or run part of it using Spark. You may have some null joins, you may have too small or too large participants. So those are the type of things that you can check when you get out of memory errors. So I'm going to stop here. I know I ran over time. I apologize for that. And feel free to drop if you have other commitments. Otherwise, I'm opening it up for questions.
Thank you, Saad. We did have one question from the beginning of the session. Evan asked if, you had mentioned dropping columns prior to doing things in PySpark, and there was a question about whether or not this is advisable when using SQL as well.
Yeah, definitely. I think it's the same principles whether you use SQL, Python, or R. In fact, you can drop the columns using the same transformations, just like I did here, meaning just selecting the columns of interest, or you can create an intermediary data set with only the columns you need, and that would be your input data set for your analysis. That's also generally a good practice.
Saad, can you see the Q&A, or do you want me to read them?
Do you
Actually,
mind
I'll read them,
reading
that way they're on the video. Hannah asks, how does a small table wind up with 200 partitions? What causes that error to occur? Or what causes that to occur?
Generally, some of the tables that you have in the enclave are built after like using complex pipelines with many transformations upstream. And in some of these transformations, when you perform a join, Spark does some reshuffling. And then after the reshuffling, it kind of decides how many partitions it saves the results to. So while sometimes it's done in an optimal way, there are cases where doing these transformations, and it might happen to you during your analysis, you have multiple steps, and then you have some intermediary steps where you do some joins and aggregations and operations, and your resulting data set, the default way is to save it into a number of partitions. That might not be optimal. It could be for several reasons. But if that's the case, it's usually good to check and try to repartition it and rebalance.
Very good. While we wait to see if anybody else has any other questions, please feel free to post them in the Q&A. I'm going to do a quick screen share here, Saad, because I found, since a lot of folks had answered in the poll that they use R heavily in their workbooks, but they are not that familiar with the Spark R library. I have scoured the web for some different tutorials on using Spark R, and I remember that there was one that I liked better than others. So I just wanted to share it and get it on the video for folks. This is produced by the Urban Institute, and it covers quite a number of sort of basics of how it works and useful operations and things, though I think it doesn't address many of the optimization techniques that you talked about in this video. So it'd be good to keep those in mind as you go through this. Anyway, GitHub, Urban Institute, Spark R tutorials. Amit asks, is there a shareable useful operation functions in Enclave? I'm not entirely sure how to.
I think my understanding of the question is whether some of these techniques and some of these logic is shareable. If you check the knowledge store, there are some templates, which are basically pieces of shareable code that you can reuse. I'm not sure if that answers your question. I can share my screen and show the knowledge store. But a lot of this code in Code Workbook, you can actually package it into a template and share it so that other people can run the code without having to rewrite it or even be familiar with it. I hope that answers the question. And I'm going to show real quick how to get to the knowledge store. And while it's loading, I just wanted to mention, if there are no other questions, obviously these are, if you go through the troubleshooting steps described in the document, but you still have issues, don't hesitate to reach out to us, and we can help you troubleshoot your errors. So in the knowledge store, this is basically a piece of shared logic where, for example, this is the one where we're performing a sample of the code. And so, actually, sorry. This is what we call a template or a knowledge object, which is a piece of shared logic that you can reuse. If you click on it in here, and you look at the code, this is basically the code that is run in this template. And you can click on action and click on use in code workbook. And you'll be able to reuse the same code in your code workbook without having to rewrite it. This is written in R, but there are other pieces that are either SQL, Python. Feel free to check this out. I hope that answers the question.
I think that more or less wraps up the questions. If anybody has any last minute ones, now's the time. Other than that, I would like to thank Saad very much for sharing his knowledge about all things Apache Spark and the Enclave. And if you have any further questions, we have office hours on Tuesdays and Thursdays at 10 a.m. Pacific or 1 p.m. Eastern, if I did my math right. Any final notes, Saad?
No. Thank you everyone for attending. I hope this is helpful. We're always open for feedback if anything is unclear, and drop into things like orientation, office hours if you have issues or filing issues. Hopefully the learning curve will be less steep.
And those are listed on the N3C calendar at covid.cd2h.org/N3C_calendar. All right. Thank you all.
Thank you.